When you run a program, something quiet but dramatic happens behind the scenes. Your code doesn't just begin executing, it is copied into memory. And from that moment on, everything your program does depends on how it uses RAM. Most developers think of memory as an infinite, invisible resource. But in reality, memory is one of the most important and most misunderstood parts of computing. It determines whether your program feels fast or sluggish, stable or fragile. Bugs, crashes, and performance problems almost always trace back to memory, even when they don't look like they do. Let's start with what RAM actually is. RAM is where your program lives while it is running. It holds the instructions your CPU executes, the variables you create, the objects you allocate, and the intermediate values used in every calculation. Your hard drive stores your program. RAM is where it becomes alive. When you launch an application, the operating system does not just give it some memory. It creates a virtual address space just for that process. Your program believes it owns a huge, continuous block of memory, even though physically that memory may be scattered across different chips. The OS maps virtual addresses to real hardware behind the scenes. This illusion is why programs are isolated. Two programs can both think they are using memory at address 0 without colliding. If a program tries to touch memory it does not own, the OS stops it. That crash is not a failure. It is memory protection working as designed. Once your program is running, memory begins filling immediately, but it does not all go into one place. RAM is divided into regions that serve different purposes. Two of the most important are the stack and the heap. The stack is where function calls live. Every time you call a function, the system creates a stack frame. That frame holds the function's parameters, its local variables, and the address it should return to when it finishes. When the function returns, the entire frame is removed in one operation. This makes stack memory extremely fast and predictable. The heap is very different. The heap holds data that must outlive a single function call. Objects, strings, arrays, lists, and most things you work with in high-level languages live there. The heap is flexible, but it is messy. Memory on the heap is allocated and freed at unpredictable times. The real difference between stack and heap is not speed. It is lifetime. Stack data lives as long as its function. Heap data lives until nothing references it anymore. That brings us to references. In modern languages, variables usually do not contain data. They contain references. A reference is a pointer to an object that lives somewhere else in memory. When you pass an object to a function, you are not copying it. You are copying the reference. Both variables now point to the same memory. This is powerful, but it is also dangerous. As long as even one reference exists, the object stays alive. If you accidentally keep a reference to something you no longer need, it will never be collected. This is how memory leaks happen in garbage-collected languages. Garbage collection exists because the heap cannot clean itself. As your program runs, it creates objects. Some are still needed, some are not. The garbage collector pauses execution, scans memory, finds which objects are still reachable, and frees the rest. This is convenient, but it is not free. Every collection costs time. Programs that allocate and discard many objects cause the garbage collector to run more often. This creates pauses, CPU usage, and sometimes stutter. Memory allocation patterns matter more than raw memory usage. Large objects are especially expensive. When you allocate something big, the runtime must find a contiguous block of memory large enough to hold it. Over time, the heap becomes fragmented. Even if you have enough total memory, finding one clean chunk becomes harder. The garbage collector may need to move objects around to defragment the heap, which means more pauses. Memory also has another enemy: speed. RAM is much slower than the CPU. To hide this, CPUs use caches. When memory is accessed in predictable patterns, the cache works beautifully. When memory is scattered, performance collapses. This is why arrays are fast and linked lists are slow. Arrays store elements next to each other in memory. Linked lists scatter nodes all over the heap. The CPU keeps missing the cache and stalling while it waits for data. The same is true for objects. Many small objects spread across memory perform worse than fewer large objects packed together. This is why object-oriented code often uses more memory than you think. Every object carries overhead. Type information, headers, alignment padding. 1,000 tiny objects cost far more than 1,000 integers in an array. This is also why value types are so powerful. When you use a value type, the data lives directly inside the variable or stack frame. No heap allocation, no reference. Better cache locality, less garbage collection. This is why modern languages are pushing towards struct-based APIs. Memory affects multi-threaded code too. When threads modify nearby memory, they invalidate each other's cache lines. This is called false sharing, and it can destroy performance even when there are no locks involved. Even simple things like string concatenation are memory problems. Each new string is a new allocation. That is why builders and buffers exist. They reuse memory instead of constantly creating garbage. Now consider what happens when RAM runs out. The operating system starts using virtual memory. It writes parts of RAM to disk and pretends they are still memory. This is called paging. Disk is thousands of times slower than RAM. When paging begins, everything feels frozen. Memory leaks do not just waste space. They can bring an entire machine to its knees. Memory bugs are not just stability problems. They are security problems. Buffer overflows, use after free, and memory corruption are how attackers take control of systems. Understanding memory is understanding safety. This is why memory is the true bottleneck in modern software. CPUs keep getting faster. Disks keep getting faster. Memory improves slowly. Most performance problems today are memory problems. Cache misses, allocations, bandwidth limits. Your code doesn't run in a vacuum. It lives in RAM. Every variable, every object, every loop competes for space, bandwidth, and locality. Once you see that, you stop guessing why software is slow or unstable. You start seeing it, and that is when you stop being someone who writes code and start being someone who builds systems.